Hello everybody, and welcome back to PLC Programming from Scratch. This is Section 2, PLC Programming Overview. The first thing I want to do is give you a little bit of history about automation and why a PLC exists. The first thing to understand is we need machines, we need equipment, and we want that equipment to run automatically. We want to have to touch it as rarely as possible. We want machines to do everything for us. 100 years ago, if there was a machine or if there was a chemical plant and a valve needed to be opened, a person had to open that valve. If a motor needed to be started, a person had to start that motor. A few years later, we started developing circuitry that would automate those machines. Then we could use a relay or a system of relays to control timers and tell things when to happen. And we started automating. Today, we have programmable relays, which are bigger than your traditional ice cube relays and can actually hold a few lines of program that react to inputs and control outputs. The next level up from a programmable relay is a PLC, and that is a fully scalable controller that can handle up to hundreds of inputs, control hundreds of outputs, and run very complex programs, and it takes automation to its highest level. Now, the first question that people will ask when they really start learning about PLCs is, why aren't we using computers to control these machines? And when you look at the specifications for a programmable logic controller, you realize that they're vastly inferior to modern PCs. Even most of our cell phones have better processors and more memory than even the top-of-the-line PLCs in use today. The downside with computers is their instability. Computers are far more prone to crashes, power spikes, surges, different things that PLCs are very well fortified against. They're built to be very robust, to be able to endure environments with noise, field interference, variable power, and they are so simple by design that they're far less prone to crashes and glitches than a PC is. That is very important when you're controlling industrial equipment, because if a heater comes on when it's not supposed to, somebody can get injured. When a pump doesn't shut off when the pressure gets too high, somebody can get killed. So PLCs are uniquely designed for controlling equipment under harsh conditions, and they're designed to not fail, and if they do fail, to fail in the safest manner possible. So for that reason, and until the next major wave of innovation in the automation department, PLCs are going to be around for probably a very long time. Hello everybody, and welcome back. In this lesson, I'd like to introduce you to the RS Logix 500 programming environment. This is one of the more classic PLC programming environments developed by Rockwell Allen Bradley for their Micrologix PLCs and various other families of PLCs that they have. Just to give you an idea, only from Allen Bradley there are at least 4 different programming languages, and there are PLCs made by Omron, Mitsubishi, Siemens, various other companies as well, and no 2 of them really program exactly the same. But if there's one common thread that almost all of the PLCs have, it's that they run a basic form of ladder logic. Some have programming systems above and beyond ladder logic, but at the core, most PLCs do run one form of ladder logic or another. So even though we're going to be working in RS Logix 500 throughout this course, most of the concepts you see will translate very easily into other systems. So let me take a little bit of time just to introduce you to this GUI, graphical user interface, that we're going to be looking at for much of the rest of this course. Of course, you've got the standard menu bars across the top. Up in this top left block right here, we have the ability to go online, to download a program to the PLC, and to upload a program from the PLC. We can select which PLCs we're working with in the comms menu. We can look at our RS links, which is another program that governs connectivity through serial connections, Ethernet connections, which we'll be discussing later on in this course. And we can actually choose PLCs that we have and decide whether we want to connect with them, upload, download, diagnose them, things like that. To the left, we have a project navigation pane, which gives us access to basically every part of a PLC program, and we'll be getting into several of these components throughout this course. To the right, and this largest pane here, this is our code window, and this is where the magic happens. This is where all of our logic, all of our program is developed. In this window, in this pane right here, we have access to various instructions that we can drop into our program. And there are menu after menu full of various instructions, most of them given really arbitrary and somewhat enigmatic names like DLG and INT and STS, and it takes a while to learn what all of those are. The good news is 80 to 90% of those commands are things that most of us will never have to use. To write a basic PLC program to control a typical machine, you don't use 90% of the commands available to you in this environment. So rest assured, it's not necessary to learn 500 different commands to write a PLC program. If you learn 20 commands, you can probably do almost everything you need to with the PLC. Aside from those menus, we also have built into the Edit menu, Verify Project and Verify File. These come in handy because every time we write a code, every time we change an instruction, we have the ability to go through and check to see if there are any problems with our program. And right here it tells me I have an error in Program File 5, Rung 1, Instruction 2. I have 3 different errors. And when I look, Program File 5, which is what I'm in now, it's my alarm ladder. On Rung 1, that absolute value block that I added has no source and no destination, and it's not in the appropriate location on the line, on the rung that it should be. Therefore, the program kicked it back to me. It won't compile this and it won't load this. When I take that out, I verify my project again. Now it likes everything. It certainly doesn't know whether or not my program is going to control the machine the way I want it to. It can't read my mind, but it does know that as far as the syntax of the programming language goes, there are no errors, so it will allow this program to be compiled and loaded onto a system. Another handy feature that this environment has is the ability to search very quickly throughout the entire program and find by address any tag that we need. So if I have an alarm reset push button on OIT, such as this one here, and We'll get into what all of this means later on in the course, but we have an address B3123. I can very quickly just tell it to find all, which is the same as typing it up in this box and using this command here. And it will tell me very quickly, right down here in this bottom pane that appears, exactly where I can find that memory location throughout the program. It tells me what file, it tells me what rung, and it even tells me, if you see this XIO and this XIC, it even tells me what type of operation is using that address. So if I'm looking for a place where a bit is being written, I can find it very quickly. If I'm looking for a place where a bit is being read, I can find that just as easily. So it's a very user-friendly programming environment, very functional, and out of several PLC programming utilities that I've used, RSLogix 500 is probably the fastest one a person can use to develop a functionality of a PLC program. And we want to see, when a PLC program is running, how does it run? How does it flow? How do the instructions register by the controller? We've got a test program here which I developed specifically for this course, and right now I have it loaded and running on a PLC emulator. So I'm going to click on our connectivity button over here that we discussed in the last lecture, and we're going to go ahead and go online. So you see the changes. Now we're greened up on our remote run processor status, and we have a running ladder icon here. When we look in our navigation pane on the left under Program Files, we see ladders 2 through 9. When you create a PLC program in RSLogix 500, you start with ladder 2, and that's the default ladder. It's always going to be there. You can't delete it. You can't get rid of it. Any other ladders you can add if you need to, and for most programs I would highly recommend doing so. You don't want all of your code in the same ladder. It makes it impossible to use. But you're going to start at execution time with ladder 2. And when we get into the ladder in our programming window, we see the rungs numbered from 0, 1, 2, down to, I have 8 rungs of code in this particular ladder, and you're always going to have an end rung on the bottom, which really doesn't count because it doesn't particularly do anything. So starting with rung 0, this program is going to execute, and once it gets to 1, we have this command that says jump to subroutine 3. So once it gets here, it's going to come over to ladder 3, and it's going to run all the way down this ladder unless it hits another jump command, in which case it's going to return to ladder 2, go down to the next line, in this case line 2, which is another jump, sending it to ladder 4, and as you can see, then it jumps to 5, then it jumps to 6, and ultimately it gets to the end and it has nowhere else to jump. So it comes right back up to 0, and it runs through the loop all over again. So the way a PLC program runs in RSLogix 500 PLCs is it runs ladder 2, and it runs it over and over again. If it happens to jump conditionally or every time to another subroutine, it will do so. But it runs ladder 2 over and over again. To give you an idea of how often this PLC can scan a program, and each time it iterates through ladder 2, we call that a scan. We're going to look back in our navigation pane, and we're going to go up to processor status, and the third tab here gives us scan times. When we look at our scan times right now, we have a maximum scan time of 61. So what that means is this program is iterating all the way through all of these ladders to the left, every instruction on every one, and it's doing that every 6.1 milliseconds, which if you do the math and convert 6100 microseconds, I believe you come up with 6.1 milliseconds. So in a single second, this program is executing hundreds of times. It's very fast. Each time it does, it's sampling its inputs, it's writing its outputs, it's considering and changing all of its logic as it needs to, it's managing its data, and it's doing all of that every 6.1 milliseconds. So a PLC program is very fast, which is another advantage it has over using something like an Android-based cell phone or a computer. We had discussed in section 2, I believe it was, why you couldn't use a computer for controlling machinery. Once you start Microsoft Office or Adobe Photoshop on a computer, you know it can slow down considerably. A PLC is very stable, runs at a very steady speed all the time. Some things like temperature or type of program can affect it, how many PID control loops you have. We'll get into those later. There are things that can affect scan time, but not nearly as much variance as what you would experience if you were using some other type of non-dedicated controller. We have made it through section 2 of PLC programming from scratch. At this point, you really should have an idea of what a PLC is, what it's used for, when you would call on a PLC, when you would probably relegate something to a computer or maybe some simpler relay-based controls. You should feel pretty comfortable looking at the RSLogix 500 GUI, Graphical User Interface. You should know how to navigate around the program a little bit. When I click into a program file and scroll down to rung 10, you shouldn't be too lost. You should know basically where I am, how a program flows. The term ladder logic should make a lot more sense to you now if it didn't already. You've probably seen enough program now to know why it's called ladder logic. If not, the screen in front of you should give you an example. It kind of looks like a ladder. You should know that a program obviously reads starting in the first program file. It's going to read from top to bottom, starting at rung 0, going to rung 1. It's going to jump to subroutines as necessary. You know, it scans very quickly and iterates through that program several times a second. Another thing that you're going to want to take out of this section, if you're not already doing it, is when you think about how a machine works and how a process works, I want you to think about it in terms of inputs, conversions, and outputs, especially as it pertains to our PLC. What we're really doing is controlling outputs based on inputs. There's a conversion in the middle, and that's what our PLC does. It makes a logical conversion based on the inputs, based on the program. Eventually we'll see that it's also based on some operator settable characteristics, set points and inputs like that determine what those outputs are, when and how they do what they do. So once we really start looking at a process as input-output conversion, this PLC programming is going to start making a lot sense, and we're going to start writing and understanding and creating logic a lot more naturally. So stick around. In the next section, we're going to get into I/O. We're going to start discussing the signals coming in, the signals going out, how to classify them, and how to deal with them.